So today we are going to start with the basics or introduction to the microstrip antenna. Okay, we are going to cover various aspects related to the regular shaped microstrip antenna. What exactly a microstrip antenna is, what are the different feeding techniques, okay, why the radiation happens from microstrip antenna, and very importantly, why a new type of antenna called as a microstrip antenna, or even in the literature if you see, it is also called as a patch antenna. So why that kind of antenna is being developed and designed, all those details, all fundamentals related to these basics of microstrip antenna we are going to cover. Our main stress or main focus will be on the regular shape designs. Okay, as you will know that microstrip antenna can be of any shape. So our main focus will be on the regular shape designs. But with respect to the projects which you do in your undergrad or postgrad or even at PhD level, different irregular shape microstrip geometries also will be dealt with. So in continuation with the regular shape microstrip antenna, we will be covering few of the modified regular shape microstrip antenna designs. So different details related to that, those design aspects we are going to cover. So let's start with the introduction or basics of microstrip antenna. So what all we are going to cover today? We are going to have an introduction to what exactly a microstrip antenna is. Then what are the different feeding techniques, because as you know you need to feed the antenna. If you have seen a dipole antenna, it's a linear wire antenna, there a symmetrical feed exists that you will be studying in the linear wire antenna or the wire antenna case. So what kind of feeding techniques are there for a microstrip antenna? Those feeding techniques we are going to study in this feeding techniques details. Later on, we will just touch upon what are different method of analysis. For example, when you design any structure, okay, there are some mathematical models which you can develop. Now those models are based on certain guidelines of the structure. For example, whether they are based on the electric current or whether they are based on the magnetic current. So all those details will be dealt with respect to the method of analysis which we are going to employ for design and development of microstrip antenna. In fact, nowadays a lot of simulation softwares are used, and these simulation software use one of these method of analysis. So that also I will try to touch upon which simulation software uses which kind of method of analysis. Again, we are going to have a brief introduction to that, because as itself the method of analysis topic is very vast. Individual method, individual analysis is a topic itself. So we are not going to get into the details of this method of analysis, but we will touch upon, we will try to understand how the particular method of analysis is employed. Okay. Then very importantly, we are going to study three types of microstrip antenna. They are regular shape, rectangular or a square, a variation of rectangle, a circular microstrip antenna, and a equilateral triangular. And then compact variations of those microstrip antenna we are going to study related to the design as well as testing. So this is with respect to regular shape microstrip antenna. Now let's start with what exactly a microstrip antenna is. Now if you recall different types of antennas which you have a dipole antenna, you have a horn antenna, you have a reflector antenna, you have a helical antenna. Now why microstrip antenna is designed? First of all, how the thought process came that a patch, something looking like this which is there on the slide, really radiates. Now first let's understand the initiation process of why this microstrip antenna was invented. Way back in 1970s, around that time, one scientist called Deschamps, actually he invented or he came across a radiation from the printed circuit board. Now the microstrip antenna, the top view and the side view, I have shown it over here. It looks like some board which is there, which has a copper on two slides. Okay, so it's like a printed circuit board. So there a scientist came across some kind of a radiation which is happening from the printed circuit board. Now that radiation, remember, antenna is a device. Like you have studied a radio frequency circuit design, in that you must have mentioned a topic related to the microstrip lines or a transmission line. Remember, those transmission lines are the elements which guide the energy within the circuit. Like whenever you are designing an amplifier, when you are designing a mixer or whatever, they are all circuits. In that, microstrip lines are interconnected. They are interconnecting these devices. So their job is to guide the energy. Their job is not to radiate the energy. And the job of the antenna is to radiate the energy. If I really go to the basics of what is the definition of antenna, I'll define the antenna like this way. It is a transducer. But remember, it is not a transducer which converts one form of electrical energy, one form of energy rather, into a different form. It is the transducer which converts the guided energy into the radiated energy. So, antenna is a transducer which is converting that. Now, what is the guided energy? Guided energy is there in the transmission line. Guided energy is there within the microstrip line. So there, this guided energy which is bounded, I also call that as a bounded energy. Why? It is residing within the structure. Okay, structure is microstrip line or a transmission line. Transmission line structure, two wire lines are there. Microstrip line, you have a printed circuit track which are laid down on the printed circuit board. Within that, the energy is confined. So there, energy is bounded. Job of the antenna is to radiate. Okay, job of the antenna is to radiate the energy and make it unbounded. Then only it will reach to a distance receiver. Otherwise, it will not. It will remain confined. Okay, so this is with respect to the antenna. So with respect to this structure, radiation was sensed, a radiation was felt, and then that led to the design and the development, and the entire thought process got evolved. Whether can a printed circuit board can be used as a microstrip antenna design. So that is the first initiation process. Remember, it is literally 6 decades back. Now we are in 2025. So much design and development have occurred. In fact, in the next few slides, I will be talking about advantages and disadvantages. Remember, whenever you come across any new design, you are bound to produce these advantages with respect to the predecessors, or you are going to say some of these disadvantages. But remember, those advantages as well as disadvantages, they are maybe talked about in 1980s or 1990s. No more, now they are the disadvantages. Okay, some of them may remain to be a disadvantage. In next slides when it comes, I will discuss more on that. So this is a microstrip antenna. Now why? I have explained you how the initiation of the microstrip antenna took place. Okay, a person came across a radiation. Now that is one side of the story. Now why there is a need? Even if you see a radiation, why to design and develop a new kind of antenna? So one thought process is, if you look at this structure, which is a simple structure of microstrip antenna in front of you, it is a planar structure. Now just imagine, antenna is a wireless device. So it has to be mounted on any wireless link application. Now let's take an example of the aircraft, or let's take an example of your mobiles. Now earlier days mobiles, if you see, there used to be some protruding structure for the mobiles. Earlier days laptops or the desktops which you have used, for a Wi-Fi connectivity, you need to have some kind of an external adapter, external connection made onto that structure. Then only the wireless connectivity was achieved. Similarly, just imagine the aircrafts. In the aircrafts, if I just going to put the antennas like a horn antenna or a dish antenna or maybe a dipole, they are basically the mounting of those antennas on those structures may cause disturbance into the planarity or disturbance into the properties of the unit. For example, if there is an aircraft, you are putting these antennas, say a dish antenna is put, then it is going to disturb the aerodynamics. If you put the dipole or the wire antennas or any other variations on your mobile sets, like you just compare yourself, earlier days mobile sets when they were first introduced and nowadays mobile sets, you never make out where the antenna is in the present day mobile set. Same thing is applicable to your laptops, same thing is applicable to your desktop or any other units which are basically personal communication devices. So nowhere you see these antennas which are external elements to the structure. They are all within somewhere in the structure. So definitely it gives some kind of a system on chip integration. Remember, integration of the entire thing on one board, that is called as a system on chip integration. So that is not really possible using your regular antenna variations like a dipole antenna or a horn antenna or any other kind of variations. Other aspect is the properties of the hosting surface. The one example which I told you is the aircraft. Let it be a satellite also. Nowhere the properties of the hosting surface should be disturbed. So in regard to this, a microstrip antenna is a unit which appears to be, like it is there in front of you, it appears to be a planar structure. Okay, a planar means a printed structure is there, it is a planar structure. So when you mount it on the say aircraft body or a satellite, or when you put it inside the mobile phones or laptops, either it will not disturb the properties of the hosting surface, neither it will protrude out from your personal device. So in those regards, this antenna has a unique advantages. There are other advantages also. In due course of time I will touch upon that also, like a circular polarization, multi-band antennas and everything. So all are these advantages actually edge microstrip antenna with respect to its other antenna variations. So that's why microstrip antenna is a more familiar or more widely used design, especially whenever a conformality or a low planar design is needed. Okay, so this is the microstrip antenna design in front of you. We are going to talk with respect to a rectangular microstrip antenna, like why it is a rectangular. Now remember, this is a microstrip antenna. This is the top view, this is the side view. This is a ground plane, this is a coaxial feed, a feed which is connecting or exciting the patch, and this is the radiating shape. Now, there are following design aspects which are there related to any microstrip antenna. What are those? First is the radiating shape which is there. What kind of a radiating geometry? Because that ultimately radiates the energy. What is that geometry we are using? Next is what is the ground plane design features? Whether the ground plane is circular, whether the ground plane is rectangular, or any other modifications which are employed in the ground plane. In fact, defected ground plane structure is one of the favorite topic for many antenna researchers, because using that one can achieve compactness, one can achieve low cross polar radiation, one can achieve bandwidth enhancement. So all these features are possible when I change the ground plane. From the basic understanding purpose, we are not going to get into those defected ground plane structure antennas. We are going to have a conventional ground plane antennas. Means they are conventional in the sense there is no modifications employed onto the ground plane. So ground plane design also has a lot of role to play in the design and design aspects or design features which you extract from the microstrip antenna. And the other aspect too is what is the feeding technique what we are going to use. Okay, right now on the slide you see a coaxial feeding technique. This feeding is very similar to a coaxial cable or a coaxial connector what you use in your laboratory. Okay, so it's appear to be a center conductor, then there is a substrate, and then there is a outer conductor. Similar to that you have a coaxial feed. So that is one of the feeding technique which is there. Then the next part is the substrate. Remember, microstrip antenna is fabricated onto the substrate, okay, or onto the printed circuit board. Now that substrate design, choice of that substrate is very critical from the design features or the antenna parameters which you obtain. Okay, like, because see, as a layman, when you want to design an antenna, or as a layman what you want to know, what is the size of the antenna, what is the operating frequency, very importantly what is the radiation pattern, what is the gain which you can get, because from the practical applications whenever I am deploying that antenna in any particular device, these two parameters are very important: radiation pattern, gain, as well as bandwidth. So for that, choice of substrate is very critical. Choice of substrate is very critical. So there lot of design aspects, or rather lot of selection aspect goes into what kind of a substrates are used. Another thing which is there is very importantly is the cost. Remember, in lab we use FR4. Okay, they are a very cheap substrate. For example, if I go to the market and if I purchase a FR4 substrate, maybe a 1 feet by 1 feet may cost me around 300 rupees. Whereas against that, if I use very efficient microwave substrate, because remember, the choice of substrate not just depends upon the application, it all depends upon the frequency of use. If I am designing my antenna around 900 megahertz, FR4 may work well. But if I am designing my antenna at 10 gigahertz, then definitely FR4 is not a good choice. Why? Although it is cheap, but it is a very lossy substrate. Okay, very important parameter comes for the substrate is the loss tangent. So it is a very lossy substrate. So definitely we do not use this substrate, especially at high frequency. Or if you want to design the efficient antenna, FR4 substrate is not used. Why? Because it has a very high loss tangent. Okay, that loss tangent is around 0.02. But from the concepts for proving purpose, or if you want to design a low cost solution, definitely a glass epoxy substrate is preferred. There are other ways of using the same FR4 substrate into the efficiency enhancement mode, that is the air suspended design, that I will tell you in due course of time, because in most of the practical projects what you are going to do, you are going to use this FR4 but in the air suspended mode. Okay, that design I will tell you later, especially when we go to the broadband microstrip antenna as well as circular polarized variations. So choice of substrate is something very important from the design of antenna. Now what are different substrates which are available? You have, as I mentioned, I have FR4. Okay, that is a very cheap substrate but very lossy. Okay, from the low cost solution, that is the one which we use. In fact, for all lab design purpose, we use this FR4 substrate. Okay, another substrate which is there is RT duroid. Okay, dielectric constant is 2.33, tan delta is 0.002. Okay, or 0.001. That range is always given. And the substrate thickness, it comes in different variations. I can have a 1/16 inch substrate, or I can have a 1/32 inch substrate also. Okay, so generally we use a FR4 substrate or RT duroid which has a substrate thickness of 1.6 mm. Okay, so this is one substrate. Again, RT duroid comes in different variations. If you just Google it, you will see there are different RT duroid substrate variations are available. RO, RT, those variations you will see. There, what difference comes is the value of dielectric constant. In fact, you can order a sample RT duroid substrate from their manufacturer. They can provide you a sample sheet. Okay, so there when you decide or when you go for a sample sheet, different variations are there. RO substrate whether you are going to select, RT substrate you are going to select. What difference makes over there is the dielectric constant. One is having 2.33, another one is having 3. So that is the difference comes with respect to the substrate. Another substrate which is there is Arlong. Another substrate is there is Teflon. So these are different substrates which are possible. Widely, we do use air as a substrate. Okay, what we do, we just suspend this patch in the air above the ground plane. So air is also used as a substrate. Now air is the most cheaper substrate which is used and most efficient. Okay, there are some other disadvantage of air substrate that we'll see later when we actually design a rectangular microstrip antenna. Okay, there you will come to know what is really a problem with respect to air as a substrate. Okay, so air can be used. Another variation again which is widely available, especially in packing industries, that material is used, is the foam. Because what happens is, if I am using an air substrate, I am suspending this patch above the ground plane. So some kind of a support is required. Other than that, I can use a foam substrate. Foam has a dielectric constant of 1.06, close to that of the air. Whereas the tan delta, the loss tangent is 10⁻⁻⁶, almost 0. So with these properties, it actually replicates the properties of the air, and hence foam is also used as a substrate. Now what additional advantages pays off? It is basically residing between the patch and the ground plane, so it provides some kind of a support. So it provides support for your radiating patch. Okay, so this is all about the substrate selection. Whenever you are designing a microstrip antenna, substrate has to be selected with respect to whether you want to go for a lossy one or a non-lossy. Non-lossy, definitely the price is there, because if you just go and purchase RT duroid substrate, it may cost you around 15 to 20,000 for 1 feet by 1 feet. That is the cost of the RT duroid substrate. Okay, so as the efficient design you go for, definitely the cost you pay more. Okay, another variation is generally we use in the design. I personally prefer using FR4 substrate, but in the air suspended configuration. So I use a combination of air as well as a FR4 substrate. So in this process, I am actually using a low cost substrate, but use of air suspended design actually makes the composite dielectric or a composite substrate properties close to that of the air. How that is done, that again, as I mentioned, we will do in case of broadband microstrip antenna design or any other variations, because air suspended substrate is very important, especially from the reliability perspective. Now what is reliability? See, reliability is very important aspect from any design or any manufacturer point of view. So suppose you design the antenna today on FR4 substrate, you just put it in your shelf and take out that antenna maybe 10 years later. Whether it will give me the same frequency, whether it will give me the same bandwidth, you cannot guarantee. Why you cannot guarantee? Because the substrate parameter may change over a period of time. Okay. Another thing, whenever you go to the market and purchase a substrate, although you say मुझे 4.3 I want that substrate, but no manufacturer does not give you the guarantee the value of that substrate will be 4.3. It always specifies the range. So the value of the dielectric constant which you go, whatever you purchase it from the market may vary from 4.2 to 4.6. Okay, so there that variation happens. Now when those variations happen, another parameter is the loss tangent. Loss tangent also can vary, although you are saying 0.02, but it can be 0.015, it can be 0.01. So all these variations actually changes the antenna parameters. So if that changes, definitely if you design for, if you are not getting, then your system performance does not meet. Means what? I am designing the antenna for a given FR4 at 900 MHz or 915 MHz, that is a GSM band. But with respect to that, because of the substrate parameter variation, if that frequency is not matched, then all my other system requirements are not matching. And that is why the substrate parameter should be as per what I am selecting in the simulation or calculation. For that, I need to ensure that my antenna parameters are independent, okay, are independent of any variation which is expected in these substrate parameters. For that, air suspended substrate provides the solution. So air suspended design not only provides you the option of realizing a low cost solution, but it also improves, this line is very important, it also improves the reliability of antenna parameters against substrate parameter variations. How? Again, that we will see more in the broadband microstrip antenna design phase. So that improves the reliability of the microstrip antenna against substrate parameter variation. This is very important design aspect. So we have touched upon what are the different things, what are the different features one should look out for a substrate selection. In the lab, maximally we use FR4 because as I mentioned, RT Duroid R-long is very costly. Many of the times we do use the air also as a substrate. In fact, if you see these repeater antennas of the Wi-Fi station, the Wi-Fi connectivity, you will see if you just break one of those antennas, don't do that. But if you will see, an air suspended patch is being used. Okay, so this is all about substrate. Now let's go to the radiating patch. Various shapes are there. Various shapes. In fact, ideally speaking, or even practically also, I'll say, microstrip antenna radiating patch, which is there on the top of the substrate, which is the one who is responsible mainly for the radiation. Mainly I am saying because ground plane radiation also occurs. Okay, so here different shapes of the radiating patch are possible. Right now, to start with, we are going to consider rectangular, we are going to consider a square or a equilateral triangular or a circular or variations of that. That I will just touch upon today in the end of the lecture. So here regular shape variations are preferred. Why? Now why regular shape variations? In fact, a microstrip antenna can have any orbit shape. In fact, letter shape microstrip antenna as per your name also can be designed, and every shape, remember, every microstrip antenna shape will have its own unique properties. Let it be with respect to the broadband design or a compact design or a circular polarized or a dual polarized, whatever. Every shape has its own design properties. Okay, but from the design perspective or from the simplicity point of view, we use regular shape. Because as everyone knows, it is very easy to draw a square. It is very easy to draw the rectangle or a circle or an equilateral triangular. Another very important aspect is when we actually touch upon the method of analysis, one important aspect is the method of analysis. You have defined functions, you have defined libraries for these regular shape geometries. Otherwise, if I just realize, say for example, if I just realize a ring, remember, there are no defined functions, standard functions which are available directly for the circular ring or a rectangular ring as against a circular or rectangular patch. So there, defined functions are not available, then numerical techniques are not directly applicable to these modified shapes. So from that analysis point of view also, when we just touch upon in the method of analysis case, having a regular shape makes the difference. Okay, it makes your analysis very simple, and thus from that perspective we are going to design a regular shape microstrip antennas rather than an irregular shape. But no one stops you. In fact, in the today's era, when you have so much of simulation software, so much of simulation computational power which is there with you, you can design any orbit shape. Okay, you can design any 3D structures. In fact, nowadays surface mounted or spherical mounted antennas are also available, because remember, microstrip antenna, I'll just touch upon that aspect later. Microstrip antenna now need not be a planar configuration. You can imagine a sphere. On the boundaries of that sphere also I can integrate microstrip antenna, because depending upon the requirement, depending upon the application, I can realize different microstrip antenna shapes as well as on different geometries. One of them is the spherical microstrip antenna configuration. So all those things are possible. So there different shapes are required. So we generally prefer, from the basics of understanding point of view, we will prefer regular shape, but no one stops us, especially in the simulation era, to use these advanced shapes. Okay, so this is about the selection of the regular shape or the shape of the microstrip antenna. Now before going further, I just want to introduce one concept, why this antenna radiates. Now just look at, in fact there is a better way of explaining the radiation. Okay, there is a better way of explaining the radiation, because remember, radiation is a loss. Okay, if you design your circuit, when you design an amplifier, remember there is a loss or a heating take place. That heating power is a I square R loss which is there. That is not usable power. It is a dissipation. Only the usable power which is getting dissipated in the load in the form of audio amplifier or whatever, that is a usable power. This is a loss. But remember, from the antenna designer perspective, this loss is very important, because ultimately it is getting detached from the circuit. So this loss is something, as an antenna engineer, I look out for. So now look at this structure. It is, from the side view, it is very similar to the parallel plate capacitor. Okay, this structure is very similar to the parallel plate capacitor. Right? Now parallel plate capacitor, what is the capacitance equation? C is equal to A epsilon naught by R by D, sorry, where A is the area of these two plates, okay, two parallel plates. Epsilon or epsilon R it is called as, is the dielectric constant or relative permeability, permittivity, and epsilon naught is the permittivity of the free space. D is the spacing between these two plates. Now just imagine capacitance. This capacitance equation tells you the charge storing ability of your device. Okay, charge storing ability, remember. But I want to remove that charge storing ability. I want to reduce that charge storing ability. Then only that charge will be leaked out into the free space. For that, what I do, microstrip antenna, generally I use a lower dielectric constant. I use a lower dielectric constant substrate. Means what? Earlier when I discussed about the substrate, I mentioned few of the substrate whose values are less than 5. Another substrate which are used in microstrip line designs is the alumina substrate, where the dielectric constant is 9.8, but we do not use this substrate for the antenna design or the microstrip antenna design. Why? Just refer this capacitance equation. In this capacitance equation, epsilon R is directly proportional to the capacity of your capacitor. It is directly proportional to the capacity of the capacitor. If I use higher dielectric constant, capacity is more. What capacity means? The charge storing ability of the structure is more. If that is there, then antennas are not going to radiate. Okay, antenna is not going to radiate. Thus, epsilon R higher is not advisable. I want to make epsilon R lower as possible, then only this antenna will radiate. So here what I am doing, I am actually bringing down the charge storing capacity or the capacitance of this antenna. Okay, so in that process I will make antenna more radiative in nature. Oh, okay. Another aspect is the distance D. In microstrip antenna design, generally the thicker substrates are used. Okay, H should be larger. Again, how much larger? As I mentioned in the radio frequency design course, everything in microwave, everything in antenna design is wavelength specific. Okay, how much thicker? How much thicker in terms of wavelength? Remember, a 1 mm thickness is not that much thicker at 900 megahertz, but 1 mm thickness at 9 gigahertz is a very large value. So here h by lambda parameter is very important. H by lambda parameter is very important. So there, in any microstrip antenna design, in any antenna design, this parameter gives the better understanding of the antenna properties. So h in terms of lambda has to be judged. Now for a given frequency of operation, if I increase that substrate thickness h, if I increase substrate thickness h, what it does, it reduces the capacitance, because d, that is the distance between these two plates, reduces. If that distance increases, capacitance reduces, what will happen to the charge? Charge will get disconnected from the circuit. So a crude way, I am again saying it's a crude way of understanding the microstrip antenna radiation. You go on increasing the substrate thickness, charge will leak out. And that's what essentially happens. Because see, when you go on increasing this parallel plate distance, there is a term called as the electric field intensity. What is that? Volts per meter. That weakens. So the lines of force which are there between these two plates gets weakened and ultimately they get detached. Why they get detached? Because the capacitance is eventually reducing. Why? C is equal to A epsilon naught epsilon r by D. D has increased, capacitance has reduced, the charge lines of force will get detached. So this is a crude way of explaining the radiation. There are better methodologies, better way, and one of them is basically a magnetic dipole case. That we will see later, how to understand the magnetic dipole case radiation from the microstrip antenna. Okay, so here with respect to this we conclude that substrate thickness should be very large for microstrip antenna against microstrip lines. Okay, dielectric constant should be as small as possible. So this is what that comparison was given here. See, MIC is your microwave integrated circuits. Means what? They are basically printed circuit elements like an amplifier, like an attenuator or whatever you design. Though they are planar circuits where the energy should be confined. So there, these parameters should be optimized from the perspective that energy should be confined in the structure. Whereas these parameters should be made large enough, dielectric constant should be made small enough so that the radiation is enhanced. You can see radiation is minimized, radiation is maximized. Again, these parameters may give some judgmental idea with respect to 1 gigahertz of operation. At 2 gigahertz, again the parameters will change. But eventually one should remember it should be thicker substrate for antenna. How much thicker? H by lambda should be very large. Okay, and it should be thinner substrate for microwave integrated circuit. It should maybe small than 0.01 or 0.05 lambda. Okay, so this is all about the substrate parameter selection and the characteristic. Now let's just touch upon the advantages and the disadvantages of microstrip antenna. As I mentioned earlier, advantages and disadvantages, maybe they were talked about maybe way back 4 decades back, but again few of them still remains one of the disadvantage of microstrip antenna. Let's go with the advantages over here. Here, as I mentioned, this is a lightweight and a small volume planar configuration. Okay, as the structure implies, it is a printed circuit design. Okay, it is fabricated on the FR4 or any planar substrate. So it is a lightweight. It is a planar design, unlike the horns, unlike the dish, unlike the other antenna variations. It is a planar design. Very importantly, they can be made conformal to the hosting surface. Okay, as they are planar, just imagine if I put that antenna onto the top of the aircraft fuselage, it is not going to disturb the aerodynamics of the aircraft. This antenna I can integrate with your MIC. So now that is the difference which you see. The earlier days mobile sets, the earlier days laptops, and present day mobile sets or present day laptops where no external device is being needed. Everything is integrated, and that is very important design aspect of the microstrip antenna, that is system on chip integration. So here they can be made conformal to the hosting surface, as well as they are easily integrable with your other peripheral systems, which we generally call that as a MIC or microwave integrated circuits, basically high frequency designs, high frequency circuits. Okay, so they can be made easily conformable. Very important aspect is the mass production facility. See, remember, when you just create a negative of the printed circuit board which you want to etch or any film, once printed circuit board facility is available, you can just do a mass production. So doing a mass production is very easy in a bulk, I should say, we use for a microstrip antenna design. Okay, then it comes, now this is very important design aspect. For realizing the circular polarization, for realizing the dual polarization, you require multiple antennas if I use a dipole. Okay, for example, those who have gone to GMRT, they must have seen, they say two orthogonal dipoles they have used to pick up two signals. Okay, now I'll just give one this more bit explanation here why these different polarizations are there. In your electromagnetic course, you must have studied three different types of polarization, that is linear, circular and elliptical. Elliptical is the more common one, and linear and circular are basically the special cases of this elliptical polarization where certain phase amplitude conditions are met. So here, in case of any wireless applications, remember, polarization is something very important. Antenna at the transmitter is radiating the signal. You have an antenna at the receiver who is supposed to receive the signal. But in that passage, in that line of, in that propagation path, there occurs a multipath propagation effects. That means signal is coming to multiple paths. It gets reflected from multiple objects. Unless and until there is a complete line of sight communication. But even that is not easily possible to achieve. So when signal undergoes these multiple paths, there is a bound to be changes in the polarization of the incoming wave. If that is happening, then if I have a fixed polarization antenna at the receiver, then I may come across a signal loss. Just imagine a case, okay, very practical example. You have your mobile phones, you keep it randomly in any orientation. Let it be vertical, let it be horizontal, within your pocket, on your desk or wherever. But still you receive a signal. Why? Are you ensuring that polarization of the mobile is in line with the polarization of the repeater station which is there? No. So there, the antennas which are integrated, they are well capable of receiving different polarization. And that is what is meant over here. My antenna should not only receive the linear polarization, my antenna should receive multiple polarization or multiple direction incoming signal. That is basically a circular polarized antenna. That is basically a circular polarized antenna. So microstrip antenna with some suitable modifications in the geometry, in the structure, can generate these linear as well as circular polarization designs. And that is one of the biggest advantage of this microstrip antenna. Okay, so any polarization issues which are there can be easily tackled with simple design modifications in the structure. I don't have to use multiple devices, unlike like one we have visited GMRT where we see that two orthogonal dipoles are used. Basically the two orthogonal dipoles are used to receive the circular polarized antennas or circular polarized wave. But there, with the suitable modifications in the microstrip antenna feeding structure or the geometry, using a single structure, I can receive circular polarized antenna or wave. So this is very important design aspect with respect to the design and the development of the microstrip antenna. That is the ease through which the microstrip antenna can generate a linear polarization or a microstrip antenna can generate a circular polarization. Remember, elliptical is a very common way. So when I design an antenna of any shape, elliptical is bound to be there. But you require some certain different efforts, certain different design guidelines to make them circular or to make them linear. but they are very much easily integrable or easily possible in microstrip antenna design case. Okay, so very important design feature of or advantage of the microstrip antenna. Next comes is your compactness or low profile. Again, this I have discussed a number of times earlier also, that they can be made conformal, they can integrate, and thus they are widely preferred in your personal mobile communication systems. Let it be a laptops or your gadgets or anything. So that is one of the biggest advantage. In fact, there are different techniques. A lot of research have gone into over last 5-6 decades, especially last 4 decades, on how to make them compact, how to make them bandwidth enhanced, even while reducing the size of the antenna. So a lot of studies, lot of papers are available in this case for making antenna compact, antenna broadband, as well as some additional design features like multiple dual polarization designs. Okay, so that is something very important design aspect. The last part which I have mentioned over here is ease of generation of dual and triple frequency response. Now, why this is required? In fact, this deals with the term called as the frequency agility system. What are frequency agile systems? Frequency agile systems are the one which can operate at different frequencies. Just imagine you are working at 900 megahertz. Your antenna is radiating at 900 megahertz, but some interference, some jamming occurs, and you are not able to receive that 900 megahertz signal. Then I need to switch the frequency. My transmitter or my receiver, especially my receiver, should have that adaptability to switch over the frequency. Now, if I use a fixed frequency antenna over there, or if I use a dipole or any other variations over there, then I need to either change the design, okay, and integrate multiple antennas to have access to multiple frequency band. So there, microstrip antenna comes for a rescue. A single radiating patch, again as I said earlier, for the circular polarized case, single radiating patch again with suitable modifications can provide these multiple frequency operation. Means what? 900 you have a jamming, switch over to say 1100 megahertz, switch over to 1300 megahertz. So those kind of frequency hopping is possible because microstrip antenna with dual and triple and multiband facility are easily possible using a single patch. Okay, that frequency ratio can change with respect to the antenna design what you are considering. Means what? 900 to 1100 to 1300, like these frequency hopping is dependent on the selection of the microstrip antenna patch, but that is very much possible. Now what it does, it provides the system a frequency agility, okay, frequency diversity I will say. Other part, circular polarization provides you some kind of a polarization diversity, okay, because you can receive signal from any direction. So frequency dual and triple frequency antenna provides you a frequency agility or frequency diversity where you can receive a signal from multiple bands, and that is easily possible in microstrip antenna case. So as many advantages, disadvantages stated, I will say very important design aspect is a single patch solution what microstrip antenna offers. Okay, single patch conformal solution what microstrip antenna offers with respect to a given application, and that is very, very important design aspect of the microstrip antenna. Okay, now as we have talked about so many of microstrip antenna advantages, we will talk about say some of its disadvantages. Now to just list a few, in fact they were regarded as a narrow bandwidth device, primarily attributed to the kind of substrates which they have used in those days. They were a high quality factor substrate. Hence, because you know that if the quality factor of any tank circuit, tuned circuit is very high, the bandwidth is bound to be small. So the type of substrates which they were used for that type of development design, that made them a narrow bandwidth element. But again, over the last 4-5 decades, lot of modifications have occurred, different substrates are used, different substrate modified configurations are used. So narrow bandwidth is not the case in today's scenario. Okay, lower gain, yes, to some extent it's a lower gain device because it's a printed circuit board. But again, different array configurations have been designed and developed. So no more, it really remains like a low gain antenna. You can realize a gain as high as 20 dB or 25 dB also. Okay, it may not be possible that, like for example, when we have visited GMRT, that gain of that antenna array, if you just remember, it is around 40 dBi. That kind of a gain is there. Those kind of a high gain elements may not have been designed using microstrip antenna 40 dB, 45 dB or something, but they do provide a very high gain of 20 dB and above. So low gain, although we may not realize a large gain as it could have been given by the dish antenna or any other antenna variation, especially the dish antennas, but you do get a good high value of the antenna gain. Last part, to some extent, it does remains as one of the disadvantage of the microstrip antenna, that is a low power handling capacity. Now, why it remains a disadvantage? Primarily attributed to the loss which is there in the dielectric. We have a lossy substrate. Even if I say a RT-duroid substrate, the loss tangent is still 0.002. So antenna efficiency which you get for a simple rectangular patch using a RT-duroid substrate may be around 70 to 80%. So there is some kind of a loss which is happening. So I cannot just pump in more power into this antenna so that it will damage the substrate. So that kind of limitation do occur. Especially that's why, as when we have visited GMRT, that time the person over there did mention that microstrip antenna designs are not so much used for such a high gain or such a high transmitting power. Then one of the disadvantage is this low power handling capacity. So I will say that first two disadvantages are no more the disadvantages nowadays. Okay, the third disadvantages may remain today. Maybe researcher can overcome this with this different dielectric selection, different advances which can be made into the material selection, the material properties for which the substrates are used. So those further developments can occur. So here we have talked about what is microstrip antenna. Okay, what are the different features which are related to the microstrip antenna. We have talked about in detail related to especially the substrate selection, the ground plane size, the ground plane dimensions, the types of ground planes, the types of radiating patch, okay, and we have talked about in the end for advantages as well as the disadvantages of microstrip antenna. So now we will go to the feeding techniques. That is the first part of our chapter. Okay, the different feeding techniques, and then various design and developments of that microstrip antenna we will take up in the next lecture. So today we will first only complete the feeding techniques of microstrip antenna. Now, as the name suggests, feeding techniques. Okay, these are the different ways through which the microstrip antenna is fed. Okay, different ways through which the microstrip antenna is fed. That is basically a feeding techniques of MSA. Okay, so here first feeding technique which is very commonly used, widely used I will say, is a coaxial feeding. Very simple feeding technique. You have designed a rectangular patch or any patch. Okay, you decide a point, okay, where you are going to feed the antenna. That point is decided with respect to the impedance matching which you want. Remember, it is not that arbitrarily you just put a feed point over there. If I want 50 ohm, 60 ohm, that point have to be properly decided. There are formulas, there are guidelines which are available. Based on that, you can find out the location of that feed point. So you decide a feed point location where you are going to feed, make a hole over there, okay, and feed a coaxial connector. This is one of the simplest way of feeding the microstrip antenna, called as a coaxial feeding, and very widely used in laboratory testing. Remember, very widely used. If I want to just use a single antenna testing, okay, without integrating that with the other systems which are there, okay, which doesn't require a system on chip integration, then microstrip antenna using a coaxial feed is the most commonly used. In fact, in most of your projects, we are going to use this coaxial feeding technique. In some of the cases, we will use this proximity also. That I will tell you bit later. Okay, so coaxial feeding technique is the most simplest. Now what are the disadvantages? Because see, there are 4-5 feeding techniques which are there, which you are going to study here. Those techniques are not just developed because like one felt ki technique, this technique has to be developed. They are not developed like this. Second technique is developed with respect to the disadvantages of the first one. The disadvantages of the first one have been overcome, and then the second technique was developed. So here, now we say what are the disadvantages of this technique. The first very important disadvantage is, if I want to do a system on chip integration, it is not easily possible for the coaxial feeding technique to do this system on chip integration. Means what? I cannot integrate. I want rest of the circuitry should lie on the same PCB, and that output of that rest of the circuitry should be fed to the microstrip antenna. That kind of direct possibility is not there. That kind of a direct possibility is not there. So if I am designing a system, if I am designing a complete RF system where antenna should be integrated with your rest of the circuitry, that is not possible. Okay, that is not possible here. So that is one of the disadvantage. Another disadvantage, you may not understand it to that extent right now. If you just see the structure with respect to the centroid of the radiating patch, with respect to the centroid of this radiating patch, it is the feed is placed on one side. Feed is placed on one side. So it is called, it is regarded as a asymmetrical feeding antenna. Okay, it is regarded as a asymmetrical feeding antenna that causes some kind of a squint in the radiation pattern, like away from the broadside. This is the radiation pattern, maybe slight squint in the radiation pattern will be observed. Okay, especially for thicker substrate. Another disadvantage is this feeding technique cannot be directly used for thicker substrate antennas, because the probe inductance of this coaxial probe will limit the bandwidth. So these are some of the disadvantages. Remember, this is a contact feeding technique. Why? The coaxial feed has a direct contact with the radiating patch. So this is a direct contact feeding technique. So these are three disadvantages. First one, I cannot do a system on chip integration. Second one, definitely it is a asymmetrical feeding technique. And third one, it has a limitation with respect to the thicker substrate design. Now why thicker substrates are required? Why? Because thicker substrate provides you a wider bandwidth. That we'll see in the broadband antenna design. Okay, so thicker substrate designs, this feeding technique is not used. So now let's work upon one of these three advantages and go to the next feeding technique, which is called as microstrip line feeding technique. Okay, this is basically a microstrip line feeding technique. What is there? You have a radiating patch, you have a ground plane, but instead of a coaxial feed running below, you are having the feed coming from the edge or the side. Now this feed can come from the rest of the circuitry, rest of the signal processing unit. In fact, this can be a single PCB onto which your entire RF systems, RF circuits are residing. They are fabricated, and one of the microstrip line running from that last end device or the front end device, what we call it as, or front end amplifier, can feed your antenna. So system on chip integration is possible. This technique, as you will see later, is heavily used in microstrip array designs. Microstrip array designs, coaxial feeding technique was not so much possible, because using a single coaxial feed, I cannot excite multiple array patches. So there, microstrip line feeding technique used. You can actually design a feeding network using a microstrip lines to excite multiple microstrip patches. So microstrip line feeding is used in such cases. Okay. So again, you need to appropriately calculate. You need to appropriately calculate the edge impedance at that point of the microstrip antenna. Then design the characteristic impedance of this line and do the matching. When we later on go to the rectangular microstrip antenna case, more on this design aspects I will touch upon. Okay, so here you need to, unlike the case like similar to the coaxial feeding technique where you need to fix up where is your 50 ohm point, 60 ohm point on the patch, then drill a hole. Similarly, here you need to first calculate what is the edge impedance. You first need to calculate what is the edge impedance and then decide the impedance of this line. Because see, connecting line, as the principle of impedance matching goes, the impedance at these two junctions should be matched. So the impedance of the antenna and the impedance of the microstrip line should be same. Okay, so you need to design this impedance matching transformer sometime, or you need to design the microstrip line which has that appropriate impedance so that it can match the edge impedance of the antenna. Okay, so this is your microstrip line design, very much used in arrays. But now what are the disadvantages? Because we have overcome the previous disadvantage. What we have overcome? Coaxial feeding not suitable for system on chip integration, not suitable for array designs. So those things we have worked upon and we have removed those disadvantages. But what is the disadvantage here? Very distinct disadvantage is, remember, microstrip line is supposed to guide the energy. As I mentioned earlier, MICs are supposed to carry the energy, whereas MSA is supposed to radiate. Remember, the properties of these two elements are contradictory. They are completely opposite. Okay, one is supposed to radiate, one is supposed to guide. So here, when I am selecting a substrate, if I am selecting a substrate with respect to antenna, that is a very low dielectric constant, then on the same substrate your microstrip line is residing. So that is a contradictory thing for the microstrip line. Microstrip line requires a high dielectric constant substrate. In such cases, if I optimize my substrate with respect to antenna, even my microstrip line will radiate. Or if I use the higher dielectric constant substrate as required for microstrip line, then my microstrip antenna will not radiate. So there occurs the conflict between the roles or the properties or design features of the microstrip antenna against the microstrip line. So that is very important disadvantage with respect to the microstrip line feeding. In fact, microstrip arrays are designed, we often talk about in the literature also, or even in your work, we often talk about the efficiency aspect. If I design a microstrip array using a microstrip line feeding network, definitely the efficiency slightly reduces. Why? It primarily comes because of the unwanted radiation or the losses which are taking place in your microstrip line network. Because it is a divider, it is basically dividing the energy. Like I have just shown it for one particular patch. When we go to the array topic, there I will show you a picture where multiple microstrip patches are catered to. So there, this kind of a circuit which is deployed will bring down the efficiency, will reduce the efficiency of the antenna. Okay, so here microstrip line suffers from the disadvantage of substrate parameter optimization with respect to antenna against my feeding line. So now what we need to work upon? We need to separate out these two substrates which are there for microstrip antenna, which are there for microstrip line. That is the design and develop. That is the design for the next feeding technique called as the electromagnetic feeding technique. Now remember, the previous two feeding techniques, they are contact feeding techniques. Why? Because there exists a direct connect of the feed to the patch. The third feeding technique or the fourth one, what you will see, they are non-contact feeding techniques. There is no direct connect from the feeding patch, the radiating patch to the feeding probe what you use. I first explain what exactly this electromagnetic feeding is all about. See, here you have first of all two separate dielectrics. The top dielectric, on top of that you have a radiating patch. On the bottom dielectric, at the bottom of that you have a ground plane. Then at the top of the first dielectric there is a microstrip line running, that is a feed line. Okay, and it is exciting the patch which is there on the top dielectric, on the top substrate. So it appears that you have separated out two substrate for the radiating patch and the feed line. it appears that you have separated out substrate parameters for the radiating element and the feeding element. Okay, so the disadvantage of this is removed in this. Now, why the name electromagnetic feeding? Remember, here there is no direct contact from this feeding line to the patch. Through the fringing fields which are there at the microstrip line edges, those fringing fields, they get coupled to the top patch through the top substrate and excite the antenna on the top. So that's why the name electromagnetic, like an electromagnetic fringing. Fringing is exciting the top patch. Okay, some kind of a radiation is exciting the top patch. That's why it is called as the electromagnetic feeding technique. Okay, variations of that is the proximity feeding technique, which you will heavily use in your projects, as well as we will discuss it in broadband microstrip antenna design. So there a proximity strip, instead of the microstrip line, a strip will be used, fed using the coaxial cable, and that is used to excite the antenna. In fact, that is the very simpler and popular technique to be used in thicker substrate designs. As I mentioned earlier, if I increase the coaxial probe thickness, if I just go on increasing the coaxial probe thickness, then the antenna characteristics, the bandwidth is limited by the probe inductance. So here I can use a non-contact electromagnetic based proximity feeding technique. It can serve the purpose of this bandwidth limitation by my probe inductance. It can negate the probe inductance and provide the optimum bandwidth. So that we will see. You may not understand at this moment of time. That we'll see in detail when we go to the broadband microstrip antenna case. Okay, so here the electromagnetic feeding technique is there, and using that through a non-contact method or through the electromagnetic coupling, the energy is coupled. So we have, it appears that, again I am saying it appears that we have removed the disadvantage of the previous one, that is substrate per se. But although physically we see that the substrates are different, electrically they are not. So this electromagnetic feeding technique partially overcomes the previous disadvantage. Now why, that we'll see. See, the fringing fields from the radiating patch, they are originating from the top substrate, they are going through the bottom substrate and to the ground. So effectively in their passage, they are seeing two substrates. First substrate being optimized, the top one being optimized for the antenna, and the bottom one being optimized for the microstrip line. Naturally, the top one is very low value, the bottom one is very high value. But is the substrate as seen by the microstrip antenna is of completely low value? No, because the fringing is passing through both the substrates. Thus, it comes across a term called as the effective dielectric constant. Whenever you have a multiple dielectric interface, you need to calculate the effective dielectric constant, and that value is the lowest of the two. Always. It is actually closer to the lowest. So if I use say a air substrate here or a foam, and if I use an alumina substrate, then the value of the effective dielectric constant may be closer to the air or closer to the low dielectric constant substrate. So completely I am not using, definitely it has overcome to 80% or 70% the disadvantage of this technique. Okay, it is used in thicker substrates also, but complete isolation of the fringing field or the complete isolation of the effective dielectric constant is not done. Okay, and why that is not done? Because the ground plane is common for both. Ground plane is common. Remember, microstrip line is only seeing this substrate, but microstrip antenna is seeing both the substrate. So I now need to do something with the microstrip rather ground plane position so that complete isolation of the two substrate is possible, and that is what is done in aperture coupled technique. This is the last feeding technique what we have. Okay, of course there are different feeding techniques which are available, okay, but with respect to the syllabus goes, with respect to the topic goes, these are very commonly used feeding technique. And as you will see, the complexity of the feeding technique is increasing day by day. As you go from coaxial to microstrip line to electromagnetic to the aperture, you can see the amount of complexity, the amount of design features or complex calculations which are involved. Complex calculation means one needs to clearly decide, like for example in microstrip line feed, what is the edge impedance. In case of electromagnetic feeding, what is the positioning of that microstrip line below the patch. Lot of design aspect, design iterations are needed over there. Okay, so last feeding technique is your aperture feeding. We have just removed or we have just changed the position of the ground. In the earlier case, the ground plane was over here, we have just moved it over here. That is the only difference. But in doing so, we need to create the opening for the excitation from the feed line to the patch. For that, we have created a slot in the ground plane. So the microstrip line which was there here, we have brought over here. Ground plane which was there over here, we have brought on the top of the first substrate. The position of the radiating patch and the second substrate still remains the same. But the excitation of this now occurs through this slot. Excitation of the microstrip patch occurs through the slot. So here again this feeding technique can be used in arrays. It can be used in system because here this input can come from the rest of the peripheral devices. So I can use in system on chip integration also. Okay, only a multiple layer PCBs might be required. That is the only difference. Okay, then it can be used in array format. A complete isolation, electrical isolation of the microstrip patch with respect to the microstrip line is done. So all aspects, all criteria of the microstrip antenna feeding requirements are met over here. Very optimum feeding technique, and in fact by appropriately designing the slot we can realize a very wideband characteristics also. Okay, so this is one of the most optimum feeding technique with respect to the microstrip antenna design. But remember, the cost wise, the design complexity wise, it is the most complex one. Why? Design, in fact there is a lot of literature which is available on how the slot should be designed. What is the positioning of that? You require multiple substrates. So complexity increases. Whenever you are writing an answer to this, you should be very precise in drawing different design attributes, different design features of all these feeding techniques. Okay, a proper 3D structure should be drawn. Okay, with markings showing microstrip lines, slot positions, radiating patch, everything should be explained properly when you are addressing a question for feeding techniques. Okay, and remember you should compare also. Like for example, you should be able to compare what is microstrip line feeding against coaxial. What are the advantages of this against this? Or maybe other two, any combination. You can be asked to compare aperture feeding technique, which is the last one. Why the name aperture coupling? Because the feeding is occurring through a small hole or a slot. That is the aperture. Okay, so here we have completed your basics introduction to the microstrip antenna. We have talked about substrate selections. We have talked about different regular patch designs, ground plane selections, comparison of MIC against MSA, and then we have talked about various feeding techniques of microstrip antenna. In the next lecture, we will actually start with your first antenna design. Okay. We will actually touch upon method of analysis, and then we will start with the design of rectangular patch, circular patch and equilateral triangular patch. So here we'll stop for this lecture. We'll meet again in the next lecture. Thank you.